I'll start by saying a few words about spin glasses and replica symmetry breaking, because this is quite a complicated topic, even though the basic description is very easy. So we can start with just the Ising model, where we have spins that can be up or down and interact pairwise with interactions Jij. And the crucial part is that these interactions Jij are disordered. So some of them are positive, meaning ferromagnetic, some of them are negative. And what ends up happening on a large scale is exemplified in this triangle here. We have three spins. One pair wants to be ferromagnetically interacting, and then this pair is also ferromagnetic. Now you cannot see the cursor. This pair is also ferromagnetic, and this is antiferromagnetic, meaning that the third particle doesn't know which way to point. This is called frustration, and if this happens in a large system on a large scale, the energy landscape across the configuration space, or across the spin configurations, gets very complicated. There is no obvious best state, and you have all these local minima that are kind of good from an energy perspective, but not perfect. Now, that's a very abstract, almost mathematical picture, but it translates to many real-world problems. In particular, this is just a quadratic energy, so any quadratic optimization problem is equivalent to a spin glass. And the question of what is the shortest path for a traveling salesperson to visit certain cities is equivalent to finding the ground state configuration of a spin glass. Now, some things are known about the spin glass, and in particular in certain models. So I'll focus on the Sherrington-Kirkpatrick model, which is an infinite range system. So every spin interacts with every other spin, no matter where it is. So in some sense, the sense of dimensionality is lost. And then the Jij interaction strengths are sampled from a normal distribution, so they are random. And for this, you can actually solve the equilibrium phase diagram. So we have the temperature and then the mean, and both are normalized to the variance of the distribution. At high temperature, we have a standard paramagnetic phase where the randomness or the temperature, thermal fluctuations dominate. If the mean interactions are strongly positive, then you don't feel that there is a variance. All pairwise interactions are positive, and so this is a ferromagnet. But this region in the bottom left is the spin glass phase region. And in the normal paradigm of phases, you need some order parameters to describe these phases. And we know very well the order parameter for the paramagnetic to ferromagnetic transition. That's just magnetization. So as you cross this boundary, the system spontaneously acquires a magnetization, which is this pointing of the collective spins. But that doesn't distinguish the spin glass phase. For that, we need a new order parameter, and that's called replica overlap. So rather than looking at one system, you actually look at two systems, two identical copies that are called replicas, labeled by alpha and beta, and then you see how similar are these two systems. So in normal systems that don't break ergodicity, two identical copies will behave the same way because the phase space is explored normally. But this tries to capture then this ergodicity breaking. And specifically, the spin glass phase has non-zero replica overlap, but zero magnetization. So the spin configurations themselves are basically nonsense. There's no particular structure in them. But if you compare two of them, they have overlap. And I'll give a little bit more intuition for this overlap by switching first to the ferromagnetic phase that also has non-zero overlap. So if we just think about two ferromagnetic identical systems, after you cool down, you will find all the spins in the all-up configuration or in the all-down, or depending, you have the Z2 symmetry breaking. So if you have two copies and they are both aligned, so both all-up or both all-down, if you calculate the overlap, it will be +1. And you also have some chance of finding one system in the all-up and one in the all-down, and then the overlap is -1. So if you look at what overlap values you could find, you'll always find +1 or -1 for the ferromagnet. But in the spin glass, this is not the case. Because of this corrugated energy landscape, you can get stuck in different local minima. And so then the configuration is very different. Your overlap will be some other value. Of course, you have the chance of finding the same state twice, in which case you'll have +1, and because it's Ising, you also still have the Ising symmetry. Well, I shouldn't do all up, but some weird state and then the same weird state, or some weird state and a very different state could lead to other overlap values. And what specific overlap values you find depends on the disorder instance, depends on the location of the local minima in the energy landscape. So sometimes you find a distribution of overlap values with one peak in the middle. I'm ignoring here the Z2 symmetry, and sometimes there is more. And so it really only makes sense to talk about the disorder average overlap distribution. And for the Sherrington-Kirkpatrick model, this leads to a very smooth, continuous filled-in distribution. And that solution, or this framework, has been developed by Giorgio Parisi in the 70s and 80s, and earned him the Nobel Prize for connecting this also to complex systems. Yeah.
Just so alpha and beta here are for the same disorder realization?
Yes.
Or different ones?
It's for the same disorder realization, but two different copies of the system. And so the evolution of the system will take you into different parts of the phase space. And so sometimes that's why alpha and beta can be different states.
But so there is to make sure I understand, so you suppose at some point in time the two systems were prepared in an identical way, and you sort of cross this phase boundary, and then you wait a certain amount of time, and then you do this calculation with two different realizations, or
Yes. I mean, this actually is experimentally not so easy to do in real spin glasses, and I think that's part of the beauty of the work we did where you really have this control, but this is the picture to have in mind, which is really a weird picture, right? Normally, in physics, the symmetry that's broken is the Ising symmetry of all up versus all down. But here, the symmetry that's broken is the replica symmetry, which says that normally two replicas, two copies, behave identically. And that's no longer true. So that's usually the smoking gun of the spin glass, of course, combined with the fact that the magnetization is 0. And I show you here the overlap distribution for a ferromagnet. And for the paramagnet, where you just get random states, the overlap distribution is a Gaussian centered at 0. So in the talk, I'll tell you how we realize the spin glass in a cavity system with ultra-cold atoms. We don't realize precisely the Sherrington-Kirkpatrick model, so I'll tell you what exactly we do realize, and then show you how we observe replica symmetry breaking. So the playground is neutral atoms inside optical cavities that are pumped from the side. And some of you might well know this, that there is a phase transition that happens as you increase this transverse pump light, that at some point the atoms develop a density wave, at which point the cavity light is populated. And this can be seen by looking at, for example, the cavity light that comes out, or by the atoms. So in real space you get a checkerboard pattern which you can observe in momentum space based on the Bragg peaks, or with the cavity emission, where you can see that after a certain point, if the pump is strong enough, you get this superradiance phenomena. And what we see here, and this is from the first paper, is that you have a normal phase when the pump is weak, and then you transition into a superradiant phase. And this phase transition comes about due to the light-mediated interaction. So the picture to have in mind is that you have two atoms sitting inside the cavity. One atom can emit a photon that bounces around, and the other one absorbs it. And that way they have interacted. Now, one thing that is important to remember is that this is a driven dissipative phase transition, so it will be naturally non-equilibrium. Many of the intuition about spin glasses is for equilibrium properties. We will touch upon that, but it will be suddenly different. So this it has been a workhorse of its own sort of niche field, and most often is done with single mode cavities. And while those allow for interesting physics by themselves, What we are interested in is multimode cavities. So here is just a picture of transverse higher order modes, and by using special cavity geometries, you can make these simultaneously resonate. So then the picture is slightly changed, so this picture of the single mode cavity now has another pathway of interacting. So one atom can choose to emit in any of these modes, that gets reabsorbed by another atom. And so this pathway and that pathway will interfere to give you more interesting photon-mediated interactions. So in Benjamin's group on the experiment I worked on, we really pioneered these multimode cavities that can be tuned. So we can start with a single mode cavity where the peaks are corresponding to the different modes are well resolved, and change the cavity length such that we hit, in this case, a confocal geometry, where the length is equal to the radius of curvature, and instead you see here a sort of continuum of modes. What that means is that not only we can of course still look at the atoms, and we can also look at the light field that leaks out, but more than just temporal information, there's also spatial information, because these modes are all different. And so if you have all of the modes, it's a sort of complete basis, so you can make spatial functions as you wish. And so what we do is also interferometric imaging of the light that leaks out that allows us to reconstruct fully the intracavity field, so both the amplitude and the phase. And that will be important later. That's a picture of what the experiment looked like even before I started. So this is our cavity inside the vacuum chamber. It's 1 centimeter radius of curvature, and we can change the length by up to 6 millimeters. And so we made BCs of rubidium-87 in there using optics that is done here, and then we can drive the superradiance transition. So let me say a few more words about what this confocal cavity does for the interactions. And we have quite a body of work, so I'll try to be sort of brief. There will be a little bit of math, and then I'll offer a more intuitive picture. As I said, you have these different pathways, so the total interaction, we have to sum over all the pathways of an atom sitting at position x1, the probability of talking to a certain mode times the probability of that mode then being absorbed by an atom sitting at position x2. But there are a few complications. So the confocal cavity doesn't have all the modes. Parity is a good quantity in these confocal cavities. So there is an even resonance and an odd resonance spectrally resolved, and we isolate the even resonance. So we have to remove some of these modes, and so we have to remove the ones in the sun as well. Then there is another complication coming from the other cavity direction. So the cavity, this is the transverse plane. In the longitudinal direction, you have, of course, all these different modes with one more longitudinal node. And the thing that makes these confocal cavities, or the modes in a confocal cavity, degenerate, is that the energy of a mode depends on how many nodes it has. So if you have more transverse nodes here, as compared to there, you have to somehow pay for that energy, and that happens by removing one longitudinal node. So that's the rule of confocal cavities, that if you increase the transverse mode index by 2, you lose one longitudinally. And what that means is that if you're in the cavity center, this cavity mode has an antinode at the center, but this one has a node. And so the near confocal cavity, and maybe the colors are a little bit hard to see, is alternating between cosine and sine-like modes. And that is important for the density wave physics, because cosine and sine are orthogonal. You can only organize into one of those. You have to pick, do you want to be a cosine mode or a sine mode? And they have then different transverse modes that combine with them. So that means that we have to actually split out this sum into the modes that look like a cosine and the mode that looks like a sine. Then you look up your favorite table for Green's functions of Hermite-Gauss modes, and then it shows that you get these three terms, and so they look very similar. We have a term that depends only on the distance, R1 minus R2, a term that arises due to the mirror symmetry of the cavity, so this is just with a plus sign, And then there is this weird term that has a plus here but a minus there. And this is then all from the confocal cavity. We call this the local interaction because it depends only on the distance. This is the mirror, as I said, and this is a very much non-local interaction. And as I said, crucially, this has a different sign. So I think that was all the math, and that's maybe not so illuminating. What we can understand from this interaction also from the perspective of ray tracing. So if we look at the light that is emitted at a certain location in the cavity, in the confocal cavity, the light will form this pattern. And so when we talk about light-mediated interactions, wherever there is light, there is interactions. And so we have to see where is the light. So this spot now corresponds to the local interaction, because that's where my emitter was. This spot corresponds to the mirror interaction. And the non-local interaction arises due to the interference of these two diagonal beams. That's why you get this sort of cosine-looking interaction. And this pattern we can also understand from a bit of Fourier optics. The confocal cavity has a length that is equal to the radius of curvature. So going from the middle to the edge is exactly r/2, which is the focal length of a curved mirror. So it collimates the beam, refocuses it. And so the confocal cavity is special in the sense that the midplane is both the image plane and the Fourier plane. So everything is Fourier invariant. Of course, we don't have just ray tracing. You can look at electric fields, and there you can nicely see the interference of these two diagonal arms, where you have these blue-orange stripes that are these cosine interactions. We can put this to the experimental test by putting atoms here and driving superradiance and looking at the light that comes out. And as I mentioned, we can see the electric field. And then we see this. So we have the location where we put the atoms shows up as a bright spot. There's a mirror spot across the cavity center. And here in the background, you can sort of see it through the projector. You have stripes of alternating color that correspond to the non-local field. So by making this cavity confocal multimode, we can make this local spot very short. So this C can be 2 microns or just below, which is 1 order of magnitude below the waist of the cavity. And it also provides a sort of imaging resolution. So if we put atoms here, the spot shows up there. But if we put atoms somewhere else, the light spot will show up there. And in that sense, through the cavity, we can image as a microscope where the atoms were. And actually, moreover, you can, by comparing some phases, you can not only know where they were, but also the density wave phase they organized into, whether it's a cosine or sine mode. And then some more technical things is that also this enhances the focusing of the light into this small spot, enhances the cooperativity. So we've used the local component for other interesting work, but the non-local component is interesting from the spin glass physics perspective. Because it's a cosine, we can make it both positive and negative, and by controlling the positions, we can really dial in a certain disordered interaction. And we can tune this interaction between, again, a ferromagnet, a spin glass, or some intermediate regime that I won't really talk about. So that allows us to study this physics, and now I should say one complication arises due to the fact that this confocal cavity has cosine and sine modes. So the density wave phase can also be a superposition of cosine and sine modes, in which case the density wave can be basically anywhere. And so, because it's now a phase degree of freedom, you can think about it as a vector spin. So the angle of this vector spin corresponds to where in the cavity, modulo the wavelength, the density wave organized. And then you have to think about how do these density waves interact. It turns out that you get this kind of interaction. I'll skip this term, but you have here again, pairwise interactions that are all-to-all because the light is everywhere in the cavity. And written in the x and y components, this looks sort of familiar. So you might remember the xy Hamiltonian, it's xx plus yy. So this is subtly different in the sense that it's xx minus yy. And so I'll tell you how to think about that, but it's a vector spin living in the xy plane where our interactions are coming from the cavity light, programmable by where we put the atoms inside the cavity. And so the idea then is that we put A to B Cs inside the cavity in certain positions, do the transverse pumping experiment and catch the light that leaks out, do these kind of holographic imaging techniques to see what density wave was each individual BC, which we then maps back onto the spin degree of freedom. So a little bit about that model. It has some symmetries, and because it's a vector model, our order parameters are now also a bit upgraded, so magnetization itself also becomes a vector, and the overlap we can just do component-wise. So we have a 2x2 overlap matrix, and actually we found that for this particular model, the relevant quantities are this capital Q and capital R, which only look at the diagonal elements of this overlap. And then we can do some standard parallel tempering Monte Carlo techniques to figure out what actually does this model look like in equilibrium, just sort of trying to describe the thermodynamic limit. And you can see here the overlap distributions where the magnetization is 0 up to finite size effects, and the overlap distribution is very much not 0. So it has some structure, and the idea to have in mind, is it the next animation? No, is that sorry, the order is slightly, that if we look at just the Q direction here, we have the goalposts here at the edges and then a continuous filling in. So that's kind of the upgraded Parisi distribution, but in 2D. So then if we look at this as function of the coupling, so we can play with the mean and the temperature, we can map out the phase diagram where we see a high temperature paramagnetic phase. There are also ferromagnetic phases, but there's actually 2 of them. So when J is positive, then the X direction is ferromagnetic, whereas if all J are negative, it becomes a ferromagnet along the Y direction. So all the spins along a line either like this or like that, depending on the sign. And if there's disorder, we have this spin glass phase. So then we go to the experiment, put A to B Cs in, and then drive the superradiance transition. First, I'm showing you just positions that we picked to realize a ferromagnetic interaction matrix. And in this case, you see actually 16 spots because I showed you the full cavity plane. So there is the cavity center here, and there is a mirror symmetry because of this evenness of the confocal cavity. From the positions, we can calculate what the interaction matrix is. And then it looks like this. It has both positives and negatives, so you might be like, I thought you were going to show us ferromagnetism. Actually, this is just a little bit of a hidden ferromagnet, so I can do a local gauge transformation where I flip 4 of the spins. Then the interactions all become positive up to some small elements there. And so the technical term for this is that it's a one-component Mattis model. What matters more is what the energy landscape looks like. So the energy landscape in configuration space is exactly that of a ferromagnet being just a quadratic energy potential. So then we can switch from the intensity imaging to the holographic imaging, where now we have some colors, and this is then via the phase of the electric field related to the phase of the density wave. So we do a bit of image processing to isolate half of the half plane, and we can reconstruct the spin state, where the arrows now indicate the XY spin. As I said, we have to flip 4 of them to make it a more obvious ferromagnet, and the 4 you have to flip are exactly those. Indeed, now we see that this is an X ferromagnet. All the spins are aligned along the X direction. And we can repeat this experiment with the same initial positions many times to gather statistics, and you can see that the magnetization is either +1 along the X direction or -1 along the X direction. We also tested that this is spontaneously broken, so this is the ferromagnetic Z2 symmetry. And from the ensemble of states, so we typically take 100 spin states, we can also calculate the overlap distribution. And here is maybe a little bit hard to see, but we have a peak here and a peak there, which is exactly what you expect of an X ferromagnet. Now you might say, okay, you say it's a ferromagnet, but I don't think all the spins are perfectly aligned along X, and that's true. Part of that is because of some term that I'm skipping over in the Hamiltonian that provides a little bit of deviation, but also some kind of effective temperature in your system will also provide the thermal energy for excitations. And so what we can do is take all the spin states and calculate their energy and create a histogram like this is actually of 900 experiments, and then fit with a Maxwell-Boltzmann distribution based on the dimensionality of the energy landscape. This is captured quite well by a thermal ensemble, which is not a given at all because this was a driven dissipative experiment, but with a temperature that is quite far below the critical temperature for this paramagnet to ferromagnet transition. So that is good. Then we switch the positions of the atoms to show also this other phase where we don't have an X ferromagnet but a Y ferromagnet, and the change in positions is not that significant on this scale at least, but you can see now that all the experiments are pointing, the spins are down or up with again similar order parameters with peaks along plus and minus Y and peaks here with a similar low temperature. Yeah.
What exactly do you need to switch the positions? So what do you kind of reference it to? So the intercavity kind of landscape of the light? Or?
It's reference to cavity center.
Okay.
So the interaction, this non-local interaction was the cosine of R1 dot R2, which is very weird because it's not translationally invariant. So that means it must have a reference to something, and that's the cavity center. So R1 is relative to the cavity center, R2 is relative to the cavity center.
Mm-hmm.
And then you take the inner product, which is also kind of weird, and then take the cosine. Yeah. So they are all referenced to the cavity center, and this is then repeated per experiment, or we can move them around. In fact, you might notice our atoms are positioned by having cross optical dipole traps that we can independently multiplex. So actually here we have 2 of them, and here we have 4 of them. And so that means that your positions are a bit constrained to these rectilinear grids, but nonetheless you can find these positions for that lead to ferromagnets. Finding glass instances is easier. You just need to sprinkle them in and to get a disordered instance. So that's what we do next. Here we change the positions. I already extracted the spin configuration. You can see, okay, it's some kind of messy thing. That's, of course, generically expected because the local, the minima will be at a random location. But moreover, if we repeat this experiment with the same positions multiple times, you can see different patterns come out. So that's the example of sort of the individual replica symmetry breaking, where we can prepare an identical copy and perform the experiment. And of course, there's noise because this is a driven dissipative phase transition that brings you into different spin configurations. So that's really neat because the typical study of spin glasses happens in bulk materials where you cannot have this precise control over disorder, and you also cannot have precise microscopic readout of individual states. So to say whether or not you have replica symmetry breaking is really hard on an individual replica perspective. Of course, you can, in those systems, still look at the order parameters, and that we can do as well by just taking the ensemble of states and comparing pairwise their overlaps. And so overlaps between a state that is found multiple times. So if we do 100 experiments, this one is found, if I remember correctly, roughly 50 of them. So if we compare 2 of those, that will be on the edge, one of the constraints. But this overlap will be generically on the interior of this overlap distribution. And that's exactly what we expect of a single disorder instance. Right? So I showed you in the beginning, if you have only a single disorder instance, you'll have replica overlaps at certain values that are discrete, and depending on the instance, you might have either 1 interior peak or 2 or 3, and that's exactly what we see here. What is interesting also is that we can change sort of the behavior of the system by changing the ramp rate at which we cross the phase transition. So if we ramp the transverse pump more slowly, then we find this kind of overlap distribution where we ramp so slow that in some sense the effective temperature is lowered enough that you can actually resolve the gap between the ground state and the first excited state. And so you will always find the ground state configuration. That's why there's no more peaks in the interior. On the other hand, if we ramp very fast, then we basically get more and more random answers and the interior peaks start to disappear. So that's the perspective from the lower effective temperature. Of course, as I said, it's a non-equilibrium system, so this is a bit hard to actually quantify. Yeah.
What is kind of the mechanism that drives this acidity breaking? So you said noise to some extent, because I mean, you need something which kind of leads you to these energy values, right?
Yeah, I think this is probably one of the things that is not super well understood about spin glasses. It's hard to say. I mean, I think that technically the right thing to say is that the time scale at which you explore the whole configuration space diverges. And so in principle, you can of course get out of an energy basin and go to another one. But you just have to get over the barrier, and if the entropy is there, if your temperature is not absolute zero, but the time scale at which this happens diverges with system size because of the disorder. The energy landscape becomes more and more sort of chaotic. And it's really hard to think about even because it's a high dimensional energy landscape, so the picture I draw with the corrugations is just really wrong once you have high dimensions. And a similar story is true for the vector spin glasses. So this is one disorder instance that I repeated here, and then of course we can move atoms around again, the BEC, to get different disorder instances, and you can see different overlap distributions emerge depending on what you specifically imprinted in the disorder instance. And we can try our best effort to try and match this with some kind of theory, because from the positions we of course know exactly what the Jij matrix is, and this works with some amount of accuracy. So what I should say here is that if we do equilibrium simulations based on the disorder instance, this actually doesn't really work. It does have the correct energy minima, but the energy of them is so wrong that if you try to reproduce this kind of structure, you either need to go to very high temperature where everything is fuzzy, or if you go to low temperature, you only get the ground state. So we found better success with non-equilibrium simulations. Of course, it's a non-equilibrium system, so that's maybe not so surprising, where we try to simulate at the mean field level the trajectory of each individual replica as it crosses the phase transition. We do that many times and then compare, and this gets closer to what we see in the experiment, although some situations it just doesn't work at all entirely. And we think part of that could be due to not knowing actually precisely what the disorder instance is, because the algebraic form I showed you, this cosine, is only true for a perfectly degenerate cavity. And of course, that's never true in reality, so there might be complications from that. But anyway, we can continue this program where we keep making different disorder instances, measure them, and assemble. Then at the end, we took 123 disorder realizations, which took 2 or 3 months, to get this kind of overlap distribution after the disorder average. And so this is then the Parisi order parameter, where we see a sort of continuous support in the middle, and I'll have this on the next slide more clearly. We also see some structure that I can comment on later. If we do the mean field trajectories, it sort of looks similar in spirit, and one could say that maybe if you took a lot more disorder averages or more disorder instances, this would become even more smooth. But of course, I wanted to graduate. So the other thing that I should show you is the magnetization. So this is the overlap distribution. At the same time, from all the replicas, we can calculate the magnetization, and here we indeed see that we have zero magnetization with some finite size effects. plus non-zero overlap. So this is exactly the key features of the spin glass and replica symmetry breaking. As I said, there is this kind of stripy structure, and for that we can look at the marginal again. Now this is on a log scale, so don't be misled. There is continuous support across, but we do see some peaks, and the peaks actually happen to line up with these dashed lines, which are 9 equally spaced lines. And of course, 9 is not a coincidence, so we have 8 BCs, we have 8 spins. If this was an Ising model, where spins have to point up or down, then there is actually only 9 possible values of the overlap. So what this is telling us is that maybe in some way our experiment that was a vector degree of freedom is weakly binarized in some effective direction. But which direction? It's clearly not the x direction, because we would have seen that in the magnetization. It's some sort of other direction, and this could be either due to the non-equilibrium dynamics, or it could in principle also be due to uncontrolled terms in your Hamiltonian. I mean, if you have accidentally some cavity light that biases you in some certain direction, we think that could in principle also do something like this. But it's certainly a combination of both, because the red line here is just the mean field trajectories that also show much less pronounced, but some of this effect as well. So, okay, the next steps are to really understand better some of these non-equilibrium effects, but then it's also interesting to sort of use this as a gateway for new insight into spin glasses. So how exactly do they function microscopically? We can perform dynamic susceptibility measurements, which are fairly standard, but with individual spin resolution. So I can ask an individual spin, how do you respond to an external magnetic field? And there are other exciting ideas about not going fully into the spin glass regime, but somewhere in between the ferromagnet and the spin glass, where the energy landscape has multiple local minima, but the energy behavior around the local minimum is still relatively well behaved. These are prototypes for associative memories. So, a bit more official of an outlook. One of the things that would be interesting is to go back to Ising spin glasses. So most of the work we did was about vector spin glasses with this kind of weird pseudo XY spin. In principle, you can also make this happen with Ising spin glasses. We did some work, as well as other people, by using 2 internal states to couple in the rubidium, where you then actually have a better pseudo spin 1/2. There are some other ideas also by using slightly different cavities, still multimode, but just multiconfocal, where you don't have longitudinal both cosine KZ and sine KZ, because this vector degree of freedom came about from that. If you manage to only isolate the cosine KZ mode while maintaining the degeneracy, you can do everything I just described, but with just Ising spins. Then this was all-to-all interactions, which are the ones that have been so far theoretically the most understood, albeit also kind of in a weird way. Short-range spin glasses really have a lot of open questions. So for certain 1/r³ spin glasses, it's not even clear whether a spin glass phase exists in certain dimensions. So I think people are pretty sure that in dimensions 1 and 2, no spin glass exists. In dimensions above 6, spin glasses exist, and somewhere in between, people are fighting. So that's hard to say, and so here we can use the local interaction now. You have to make it disordered to do some experiments that can shed light. And lastly, the experiments we did were with 8 BCs. So each BC is a macroscopic spin. There are many particles. But if you manage to bring that down to the individual spin level, either by isolating single particles or by rendering each BC effectively a single degree of freedom via Rydberg blockade, then you can bring this into the regime of quantum spin glasses. And there's a lot of cool new effects. And I should also say that around this phase transition between the normal and superradiant phase in the spin glass regime, there's all kinds of interesting effects happening. So we have theoretical work from my lab mate who looked both near the phase transition, where we can see effects of entanglement, as well as far above the threshold, where the dissipation of the cavity actually can be a good thing because it naturally realizes steepest descent dynamics in the energy landscape. Normally, calculating the steepest descent means you have to try each direction and figure out which ones is the steepest, so that's computationally not very efficient. So then I will show you the team. So that's in the group of Benjamin at Stanford with the rest of the team and theory collaborators and funding agencies. And I will just show one slide on the stuff I currently do in Munich, where we are working on an ytterbium machine for quantum simulation, where we combine two very common and promising techniques. So we use 3D optical lattices and combine that with 2D tweezer arrays. So this sort of merger of technologies is quite promising, and also recently you might have seen various kind of cool advances of iterative assembly and rearrangement. And so our experiment is built for that too. In particular, we plan to use multiple tweezer arrays to create very state-dependent potentials. So recently we worked on some cooling. Everybody always wants to get cold, but we don't want to do evaporation. All we care about is getting to the motional ground state of the lattice. So there we can actually leverage the clock transition in ytterbium to perform sideband cooling. And the outlook is predominantly for simulating lattice gauge theories, but really with such a platform you have quite a lot of flexibility in terms of tweezer array versus optical lattice, and so there is a variety of other things that we intend to do. And so I'm happy to discuss more offline about this. All right, that's it. So thank you for your attention, and I'm happy to take more questions.
Questions? Zoe.
So you started sort of motivating spin glasses as encoding optimization problems. What are the prospects, if any, for using that setup for solving optimization?
Yeah, so I guess this gets very dangerous in terms of like saying what quantum effects can do in terms of helping you optimize, like find solutions more easily. The thing I would point to is in terms of the experiment. The experiments we did were not so complicated to optimize, I would say, even though as vector spins, the Hilbert space is already quite large because you don't have just up down.
What was your n, effectively?
That was 8, so we had 8 spins.
Yeah.
And then each spin was some combination of individual particles, but you probably care about
so that
number 8.
amounts to 2 to the 8
but
space, or
if
not?
it was an Ising model.
Yeah, but it's
and
not
so
Ising.
it's 0 to 2 pi to the 8th. So it's a continuous space, which means that I think it's harder to find ground states than the Ising model, despite the fact that you can do sort of convex optimization techniques. That we can debate which one is harder.
Okay, but you could prepare approximately the ground state and then you
So
could read out.
In this case, I would say, because we ramp so slow, we find always the lowest local minimum, so the global minimum.
Okay.
And in that case, then you would say you've effectively solved this n equals 8 optimization problem. Of course, that's a huge caveat that as you grow in system size, the gaps will shrink exponentially. And so this approach of going slower through the phase transition is not a very good one because you need to go exponentially slower. There are some people who think that this sort of driven dissipative picture helps you in sort of stabilizing the lowest energy state. Because you can think about the superradiance, you can think almost about it as a laser. You have some sort of gain that you can sort of start to crank up, and then there is various modes with different loss. And the lowest lying mode, the ground state, has the lowest loss. So that will start to laze first. So if you sort of, in that picture, you can have something like that's maybe equivalent to this picture of you need to ramp up the gain slow enough. There's various fields in actually sort of more optics. So there's coherent Ising machines that try to leverage this for optimization also. And I don't know how much really it's like behaves like a quantum computer in terms of optimizing. But I'm sure it can find some ground states.
I didn't even need it to be quantum, I was just curious to know.
Yeah. I think this experiment that I'm showing you here certainly went much faster than me trying to find the ground state on a computer. So I take that for what you will.
Is that you trying to find it? Or?
No, I mean me using somebody like established code for convex optimization to find the ground state.
More questions? I have one.
Yeah.
The Sherrington-Kirkpatrick model with 8 sides should have 64 independent coupling constant. But of course, I mean, because the Jij should be independent of each other.
Usually, it has to be symmetric.
Okay,
but
I mean,
yes,
give you a factor of 2, but it should scale quadratically with the number of particles. I mean, here, if you just rely on positional disorder, you essentially have one independent coupling per atom, and you don't have n squared. You have n.
You have n, yes. That's enough still. So we can, of course, it's not very hard to say, and in fact it's not really n even, because we have only the x coordinates and the y coordinates, and you get every combination. So here it was 2 y coordinates and 4 x coordinates, that's it. It's not very hard to throw that into your cosine ri.rj over and over and look at the random matrix ensemble that you get out and see whether it's truly random. And it is.
But so even if you would start to scale the number of sides, you still think that it's enough disorder that the physics will show up?
Yeah. Okay. Yeah, at least from the random matrix perspective. And I think, if I remember correctly, there's some kind of, you have to keep the density of particles the same. So like you have to also not try to cram them in the same area.
Okay.
I mean, this is already true because it's a cosine. So if you put all the clouds very close to the cavity center,
they're all the same.
It's all cosine of a small number, so that's actually just a fair amount. So you have to sprinkle them out a little bit. Of course, there are practical considerations because you cannot go outside of the cavity, but we're limited in n equals 8 more so by the atom number and the size actually of these beams, because ideally you want these beams to be very small so you can put them very close together, but in our case, the experiment wasn't designed with this in mind. So they are small but not super small. They're roughly 30 micron waist, and so we can go up to 300 micron out in cavity radius because it's a confocal cavity, so you can go pretty far out. And there is still mode support, but that already limits. I mean, you can do 5 by 10 at most. Of course, that's technological.
More questions? Okay, if I don't see any, then let's thank Ronen again.